this is B. Naresh, working as an assistant professor in EC department. The today's topic is analysis of generalized JFET amplifier. So, in our previous sessions, we observed that the analysis of the JFET amplifier in a different configurations like common source, common drain, as well as the common gate by using the small signal analysis. So, by using the small signal analysis, we derived some parameters like the voltage gain, input impedance, as well as the output impedance of the three different configurations like common source, common drain, as well as the common gate. So, before going to this, and we know that the FET means the FET is called as the field effect transistor, and based on that, we identified that. So, in that, how the drain current is controlled by an applied electric field between the two terminals like gate and the source, as well as the drain and the source. So, based on that construction of the FET, we identified that we need to apply a biasing voltage between the gate as well as the source, along with again drain and the source. So those are represented as VGS and VDS. VGS as well as the VDS. And we also know that the FET again defined as two types. One is JFET. Another one is represented as MOSFET, where JFET indication is junction field effect transistor, and the MOSFET indication is metal oxide semiconductor field effect transistor. So in that also we observe the different types of the construction based on the channel, either N channel or a P channel, either N channel JFET or a P channel JFET, like that. In the MOSFET, we observe the enhancement as well as depletion type MOSFET. And we also identified that the amplifier analysis for the different three configurations like common source, common gate, as well as the common drain, where S indication for source, G indication is the gate, and D indication is drain, and C is indication is common. So we discussed individually. So we derived that or we designed a small signal model with respect to the configuration, either in a common source configuration or a common drain or a common gate configuration. Now today we are going to discuss a generalized JFET amplifier, and by using the generalized JFET amplifier, we are going to describe or define the three configurations like this one: common source, common gate, as well as the common drain. So for this case, if we recall that either a common source or a common drain or a common gate, so based on the terminal representation of the JFET, we have the three terminals like source, drain, and a gate. So when we can say that the common source means the source is common for input side as well as output side, then we need to identify the which one remaining out of the remaining two terminals, which one is acts as the input terminal and which one is acts as the output terminal. So hence we need to assume that for this common source configuration, gate is acts as a input and the drain terminal is acts as a output. Similarly, if you are defining the common drain, so again we have the three terminals. So hence the drain is a common. We need to make the drain is a common terminal, and the remaining source and gate. So out of these two, we need to find out so which one is acts as a input side and which terminal is acts as the output side. And from this representation, so across the gate, we are going to pass the input signal, and across the source, we are going to measure the output parameter. And similarly, so if we consider the common gate JFET amplifier, so we have again three terminals: source, drain, and a gate. So hence, gate is represented as common. So this gate terminal is a common. Now we need to find out which terminal is acts as the input and which terminal is acts as the output. So for this common gate amplifier, the input is passing through the source terminal and output is measured across the drain terminal. So for every configuration, we required some amount of input voltages or input sources. If it is a common source, the input is passing through the gate terminal, and if it is a common drain, again input is also passing through the gate. But in the case of common gate terminal, the input is passing through the source. And again, from these three different configurations, the output is also measured either the source or a drain. When a output is measured across the drain, so that is belongs to either common source as well as the common gate. If output is taken across the source, that is belongs to common drain amplifier. So hence, to analyze this generalized JFET, so means from the generalized model, we can configure either any one configuration like common source configuration or a common drain or a common gate. Hence, we required a three. So the input from this we can observe to define the generalizer from these three configurations. So input is passing through gate as well as the source, and output is measuring the drain and source. So hence, I'm going to connect a three independent different signal sources. So one is in series with a gate, and one is in series with a source, and one is in series with a drain. So when the input signal Vi is connected with a gate, the voltage across the source that is represented as a Vs, and similarly here I represented a one voltage source representation, that is Va, that is in series with a drain. Then we need to measure the two output terminal representations. One is across the source and one is across the drain. Hence, now I'm going to design a generalized of JFET amplifier. And before going to this, again we need to recall the principle and what type of biasings are required to allow the conduction in a JFET. So hence, so let us consider if I consider the JFET is, we know that again the JFET is the two types. One is it is represented as N channel JFET, another one is represented as P channel JFET. And here I consider as the given JFET is acts as a N channel JFET, hence, and we know that if it is the N channel JFET, the source and drain is made up with N-type material. Hence, the conduction is depends upon the majority charge carriers, and we know that in a N-type material, the majority charge carriers are electrons. And we need to diffuse, or we need to repel the charge carriers, or we need to diffuse the movement of the charge carriers from the source to drain, then only it allows the drain current from the drain to the source terminal. So to diffuse this or to movement of the charge carriers from the source to drain, externally we need to apply some amount of energy or in terms of electric field, and that is called as VGS. And if we consider the N channel JFET, and let us take this is the gate, and one terminal is represented as the drain and one terminal is represented as the source. To repel the charge carriers from the source to drain, we need to apply a source is biased with a negative pole. Why it is connected to negative pole means, and here the source and the drain is made up with electrons, hence the majority, so the source and the drain is made up with N type, hence the majority charge carriers are electrons. to repel these electrons from the source to drain. Hence, for this electron side, we apply a negative potential energy with respect to the drain. Hence, drain is a biased with the positive pole of the battery or electric external source, and the source is a biased with the negative pole of the battery. And from this representation, so hence directly, so generally the negative energy means this is less than zero, hence it should be I consider the ground potential, and this is positive potential, hence here I consider this is the plus VDD. Let us consider, so for across the gate, we apply the input signal Vi, and similarly for a drain terminal and a source terminal is a bias with some external components, external resistances. And when an external resistance is a bias with a drain, that is represented as capital RT. When an external resistance is biased with a source terminal, that is represented as RS. And we applied a input, a voltage source through the source as well as through the drain, and through the drain that voltage source it is represented as a VA, and through the source the voltage source is represented as Vs, and the source is connected to ground potential. And from the previous observations, so what we observed from the three different configurations, the output is measured either drain or a source or whatever the configuration, either the common source or a common drain or a common gate. From these three different configurations, we observe that output is measured either across the drain terminal or a source terminal. Hence, so here I represented as the output parameters either the drain or a source. So hence, to satisfy, this is the generalized model, and to satisfy the different configurations like a common source, common drain, or a common gate, let us consider. So suppose I am going to choose a common source amplifier. If you want to utilize this acts as a common source amplifier, what is the meaning of common source? Means source is a common terminal, and the gate is acts as a input, drain is acts as a output. So hence, for this common source, input is Vi source that is passing through the gate, means remaining two voltage sources I am going to make the zero, means Va and Vs I am going to make it as a zero. If you want to utilize this generalized JFET is acts as a common source amplifier, the input is passing through the gate, hence I consider as a Vi, and the remaining two voltage sources Va and Vs I consider as a zero. And we know that if any voltage source is represented as zero, means it is replaced with a short circuit. It means simply this RT is connected to drain and RS is directly connected to the source. And from this common source representation, we know that output is measured across the drain. Hence, for this case, the output is, so across the drain, we represented some polarity, that is VO1, the output 1. So hence, we need to consider the VO1 output. So to satisfy the common source amplifier by using this generalized JFET amplifier, we need to assume these conditions. The input signal is passing through the Vi to the gate terminal, and the remaining two voltage sources Va and Vs we consider as a zero, and output is we taken as across the VO1. Similarly, if you want to satisfy a common drain amplifier from this generalized model, so common drain means, what is a common drain? Drain is a common terminal, and gate terminal is acts as a input, source is acts as a output. Hence, again, your input is Vi that is passing through the gate, and again remaining two voltage sources. What are the remaining two voltage sources? Va and Vs we made as a zero, but We know that in a common drain amplifier, the output is measured across the source. So hence, hence, what happens? So the source means across the source it connected as a VO2. Hence, the output is we consider as VO2. V0 is equal to VO2. We need to consider like this. And similarly, if you want to satisfy a common gate amplifier from this generalized model, means gate terminal is a common, source is accessed as input, drain is accessed output. So from this generalized representation, now we need to pass the input through towards the source terminal. Hence, we need to apply input is passing through the voltage source Vs, means Vi and Va we need to assume as 0. The voltage is across the Vi node and the Va node is represented as 0. And for this common gate amplifier, output is taken across the drain side. Hence, now I'm going to take the V0 is equal to VO1. So these are the three representations to satisfy the three different amplifiers from this generalized JFET amplifier. So hence, I represented the same points. For the CS amplifier, Vs and Va is a 0. Output is VO1 is taken. That is a drain. For a common gate, we need to take Va and Va is a 0. And input signal is passing through the Vs and the source resistance Rs, and output is taken as VO1. Similarly, for the common drain circuit, so already we observed it is also called as a source follower. So hence, and here we need to take RD is also 0, Vs and Va is a 0. Then input is signal Vi and output is VO2. That is taken from the source. So before going to this, to analyze means we need to satisfy from this generalized model, we need to define all the three configurations. So like common source, common drain as well as the common gate. Hence, we need to configure into a model into a low frequency model or a small signal model. So to recall means we need to convert this generalized JFET redraw into a small signal model. If you want to draw the small signal model, and we know that from the characteristics of the JFET, so what are the characteristics of the JFET? We have the two characteristics. One is represented as drain characteristics, another one is represented as transfer characteristics. From this drain and transfer characteristics, we observe that the drain current is a functioning of applied biasing voltages between gate and the source, that is VGS, and the biasing voltage is applied between drain and the source, that is VDS. And from this, based on the small signal model representation, we derive that from the Poisson's theorem equation, we derive this, the drain current is equal to, from the small signal model, ID is equal to Gm times of VGS plus 1 by RD times of VDS. Hence, and from this representation, we know that the JFET, just the circuit, means the symbol JFET, only this JFET is, so means let us consider this is the gate and the drain and the source. It should be converted into a small signal model based on this mathematical representation, that is ID is equal to Gm times of VGS plus 1 by RD times of VDS. For this case, let us take, and from the JFET, from the construction of the JFET, we know that the applied biasing voltage between the gate and the source is very, very small. That is otherwise that is decreased from the 0, means the reverse bias voltage. We apply the reverse bias voltage, hence the gate current is very, very small. Hence gate is open. Then let's say this is the gate, and this side this is the source, and output side we use the drain, and this drain current contains two current sources. One is Gm times of VGS, another one is V1 by RD times of VDS. So this is The biasing volt means the potential difference between drain and source. Now we need to redraw this generalized JFET amplifier model into the small signal model or a low frequency model by using this equation. ID is equal to GM times of VGS plus 1 by RD into VDS. Now I'm going to redraw in terms of small signal model, and from that we need to derive the parameters, means like how it will be affects on the gain parameter or a input impedance or a output impedance parameter. So let us consider. Now I'm going to a redrawing this generalized JFET amplifier in terms of small signal model. So hence, so let us consider first. Let us take this is gate, and output side I consider the drain D. Let us consider the source, and bottom one is the source. And you recall this equation, ID is equal to GM times of VGS plus 1 by RD into VDS, where so we know that GM is, where the GM is nothing but a transconductance, and VGS means the potential difference between gate and the source. Small RD means internal drain resistance. It is also called as a AC resistance, internal drain resistance. It is also called as a AC resistance. And the VDS means the potential difference between drain and source. Now I'm going to represent. So one current source is GM times of VGS plus 1 by RD times, this is small RD. Let us consider this is the source, and we have the a potential difference between drain and a source, that is represented as VDS, and we know that the potential difference between gate and a source, that is VGS. Now we need to place the remaining external biasing resistances. One external biasing resistance is across the RD. So hence now this is, let us consider this is RD, capital RD, and one more resistance is there across the source. Let us take this is the source, and this is RS, and the input is passing through between gate and the source. Let us take this is the VI, and suppose if you want to utilize this is a common gate amplifier, and this is one more voltage source is VS, and most of the cases we are not using this voltage source across the VD, and otherwise I'm going to choose this is VA, this is the voltage source VA, and now I'm going to measure. So this is VO1 parameter, and across the source resistance the output is represented as VO2 parameter. And we know that if you want to find out this one, so up to this point this is VGS, and here it is represented as VO2, that is equal to the voltage drop across this RS resistance is represented as VS. So by using this generalized small signal model, so now we need to identify the parameters like voltage gain, current gain, and voltage gain, input impedance, and output impedance. Hence, so if you observe, so from this circuit, so what we know that VI is equal to, from this circuit, VI is equal to VGS. So means up from this node to this node, that is represented as the potential difference between gate and the source is VGS. And one more is the voltage drop across the RS, that is represented as VS. Hence, I represented as VA is equal to VGS plus, that is nothing but a V0 means, So this is VO2 term. So hence this VO2 term I consider as the V0. So hence that is Vi is equal to VGS plus V0. From this we know that VGS is represented as Vi minus V0. Now we need to find out, suppose if you want to identify the VO1. So VO1 means the drain current is flowing through capital RD. And similarly, if you want to calculate this VO2, so we need to write VO2 means IS into RS. And most of the cases, from the construction of the JFET, we know that IS is equal to the summation of gate current as well as the drain current. So based on the construction of the JFET, we know that the gate current is very, very small, hence ID is a 0. IS is approximately equal to ID. So hence VO2 is represented as ID times of RS, and the VO1 is represented as ID times of capital RT. So that is the reason. So we need to find out how much drain current is the flows with respect to this all these biasing voltages and biasing components like the capital RD and RS, along with the internal resistances, that is internal due to that internal transconductance and internal drain resistance, that is small rd. Hence, so if you apply the KVL so across this output side, so let us consider, so what happens now, we need to write down the voltage drop across this capital RD, the voltage drop across the small RD, and we need to write the voltage drop across the RS, that is equal to 0. So hence, how to write this, the voltage drop across the capital RD means which current is the flows. So here it allows the drain current, hence ID times of RD. Now we need to calculate the voltage drop across the small RD means, let us say, if you assume this one, ID is equal to GM into VGS plus 1 by. You can write like this, GM VGS I represent as I1, VDS by RD I assume that I2. Now I need to calculate this I2. So means I2 is equal to ID minus I1, means this I2, here it is represented as ID minus GM into VGS, means the current flowing across this internal drain resistance, that is nothing but a I2 current. That I2 is nothing but the ID minus GM times of VGS along with the internal drain resistance, that is small rd. Then we need to calculate the how much voltage drop is flowing through this current source, the resistance RS, that is nothing but a Vs. Hence, to apply the KVL, so means we need to write here the voltage drop across the capital RD plus the voltage drop across the small rd plus the voltage drop RS, that is equal to 0. So hence, here I represented as the voltage drop across the capital RD means, so if you observe this one, now I am going to find out the voltage drop across this RD means V is nothing but a I into R. So which current is the flows? Drain current, and the resistance is RD. Hence, I represented as ID times of RD, that is equal to voltage drop across the capital RD. Similarly, we need to write the voltage drop across the small RD. Just now we observed the voltage drop across the small RD means I into RD, means which current is the flows? I2. What is I2 current? ID minus GM times of VGS. Hence, it is represented as ID minus GM times of VGS times of small RD. Along with, now we need to calculate the voltage drop across the source resistance. Hence, the voltage drop across the source resistance means, now we need to identify which current is the flows, that is IS. And generally we know that IS is approximately equal to ID. Hence, I am going to write ID times of RS. So, and that is the reason it is represented as ID times of RS. Now I can simplify this one. From this, we need to identify the how much drain current is absorbed with respect to the all the biasing components like capital RD and capital RS, along with the internal resistances, the resistance conductance as well as the internal drain resistance. So hence, so I'm going to simplify this one, ID, RD, RD, then you can multiply here. So id minus gm. So vgs means again, so what is the vgs? No, we know that vgs means the potential difference between gate voltage and the source voltage. The potential difference between gate voltage and source. So if you observe the circuit across the gate, which input signal we are passing? Vi, hence, so Vi minus your Vs. Vs means we know that the voltage drop at the source, we know that Id times of Rs. Hence Vi minus Id times of Rs. That is nothing but a VGS. Hence this VGS I represented as Vi minus Id times of Rs into Rs. Then you can this Id times of zeros. Now you can expand the term Id into small rd minus gm VIRD plus minus of minus becomes plus. So gm into capital Id into Rs into small rd plus Id into Rs. Now again, from the characteristics of the JFET, we defined one relation between the characteristic parameters. We know that one in a FET, mu is represented as gm times of rd. So where gm is a transconductance, small rd is internal drain resistance. Hence, I'm going to simplify this one. Gm into rd is replaced with mu. So here also gm into small rd is replaced with mu. So just expand the terms and simplify. So can simplify. Then from that you should identify the how much drain current is allows. Means from the simplification, what happens? This is id is equal to mu times of vi by capital RD plus small rd plus 1 plus mu times of rs. So this is we derived from the a small signal model of the generalized JFET. It contains all the biasing resistances across the source as well as the drain along with the internal parameters here. So hence now, so this is the drain current with respect to the all the parameters. Now we need to find out so how it is satisfied to either common source or a common drain amplifier. So if you want to observe the common source amplifier from the circuit, so how to observe the common source amplifier? Common source amplifier means, so in a common source amplifier also we observe the two cases. One is without source resistance, means Rs is equal to 0. And the second case when we are adding the source resistance to the common source amplifier, what happens also we discussed. So that is the reason. We need to verify the two cases, what happens without RS source resistance and what happens with source resistance for a common source amplifier. So if you want to measure the common source amplifier, the output voltage should be measured across the VO1. So what is the VO1? VO1 is equal to this one. ID times of RD. Actually, let us consider this is IL. So what happens here? This is the drain current flow direction and the load current flow direction. So hence VO1 is equal to minus, so minus ID into, otherwise you can write this VO1 is equal to IL times of RD. But the same drain current is flowing through the load resistance but in the opposite direction. Hence we can write this is minus ID into capital RD. That is the reason. For this common source amplifier, I represented as VO1 is equal to minus ID into R. So just now we got this ID is equal to mu times of Vi by capital RD plus small rd plus 1 plus mu times of Rs. So now you can substitute this ID value and you can simplify. So what happens? VO1 is equal to just mu times of Vi into capital RD by capital RD plus small rd plus 1 plus mu times of Rs. This is a minus. But it is not a negative. But here this sign indication is the 180 degrees phase shift with respect to the output and the input signal. And from this, now we need to define the voltage gain. So generally, how to define the voltage gain? The voltage gain means it is defined as it is the ratio of output voltage to the input voltage. From this generalized JFET amplifier, what is the output voltage? The output voltage is represented as VO1, hence I represented the VO1. Input voltage is VI. So what is the VO1 parameter? VO1 is represented as, so mu times of VI into RD means, so I'm going to write like this. So mu minus mu VI times of RD by capital RD plus small RD plus 1 plus mu times of RS by your input signal is VI. So hence this VI is a get cancel. Now it becomes what happened, minus mu times of capital RD by capital RD plus small RD plus 1 plus mu times of RS. So this is the voltage gain when we are considering the source resistance. So the source resistance is exists for a common source amplifier, and where this negative sign indication is for a 180 degrees phase shift with respect to the input and the output parameter. Suppose if you want to measure a common source amplifier without a source resistance, means that, so what we need to assume without the source resistance means we need to consider the RS is equal to 0 without source resistance, means we need to remove the source resistance from the source terminal to define a common source amplifier without source resistance. For this case, let us assume in a common source amplifier, if a source resistance is a 0, so what we observed in a voltage gain, that is mu times of, means AB what we observe, minus mu times of capital RD by capital RD plus small RD plus 1 plus mu times of RS. But for this common source amplifier, let if the source resistance is removed, means if RS is equal to 0, so hence in this case if RS is 0, what happens, this is minus mu into capital RD by capital RD plus small RD plus 1 plus mu times into 0. Hence that is equal to minus mu into RD by RD plus small RD. So this is answer. And so here generally we know that this is mu into capital RD by capital RD plus RD. We know the one relation. What is the relation from the characteristic parameters? Mu is equal to GM times of small RD. Hence, if you means you can rewrite this equation in terms of this one. So means minus GM into small RD into capital RD by capital RD plus small RD. So this is the voltage gain for a common source amplifier without source resistance, or when we consider the source resistance is 0. So similarly, if you want to calculate for a common drain amplifier, so in this case, let us consider if you observe this generalized model, then for a common drain amplifier, for this common drain amplifier, so common drain means the input is passing through the gate, but output is measured across the VO2. But for this common drain, again we need to assume the capital RD is 0. That is the reason. For this common drain amplifier, so now the output is measured across the source, that is represented as a V02. And generally V02 means the current flowing across the source resistance is IS along with the RS. But from the transistor construction or from the JFET construction, we know that IS is equal to the summation of gate current and drain current. So based on the construction of the JFET, generally the gate current is very small. Hence, we assumed as IG is a 0, then IS is approximately equal to ID. Hence, the VO2 or the output voltage across the source terminal is represented as ID times of RS. So ID times of RS. Now, and just now we observed ID is equal to mu times of VI by capital RD plus small RD plus 1 plus mu times of RS. Hence, I am going to substitute in a V02. So V0 is equal to ID into ID means mu VI by capital RD plus small RD plus 1 plus mu times of RS into so RS. Hence, the VO2 is represented as mu times of VI into RS by capital RD plus small rd plus 1 plus mu times of Rs. So this is VO2. Now if you want to define the gain parameter, so what is the gain parameter? Again, it is defined as the ratio of output voltage to the input voltage. Hence, if you observe this generalized model, again the voltage gain, output voltage means that is taken from the source, hence it is represented as a VO2. Input voltage, the input voltage is passing through the gate, that is represented as Vi. Hence, VO2 is mu times of Vi into Rs by capital RD plus small rd plus 1 plus mu times of Rs by Vi. So hence Vi is a get cancel. Then the voltage gain of common drain amplifier becomes mu times of Rs by capital RD plus small rd plus 1 plus mu times of Rs. So this is the voltage gain if that is measured across that is measured for common drain amplifier. But from the normal construction of the common drain amplifier, we consider as there is no drain resistance. Hence, we are going to assume the drain resistance is removed from the generalized JFET amplifier for the common drain amplifier. Hence, here assumed as the drain resistance RD is equal to 0. Just can substitute this RD equal to 0. What happens? The voltage gain is represented as mu times of Rs by small rd plus 1 plus mu times of Rs. Hence, it satisfies the normal common drain amplifier by using this generalized JFET amplifier. So, today, up to this point, today we discussed the analysis of generalized JFET amplifier. So, by using this generalized JFET amplifier, we derive the common source, common drain as well as the common gate amplifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.